I don't know if you remember when we did kinematics, d equals VIT plus a half AT squared, VF equals VI plus AT. I gave you this hook, this approach. I made up a name. I called it DFIC. It was list your data, find a formula, insert crunch. And it wasn't the end all be all, but I wanted to give you a place to start. Free body diagrams are the DFIC of this unit. If there's a single tool, Jada, that I'm going to give you that's hugely useful, it's today. And if you talk to any of my physics 12s, if you say to them, this is a job for almost every one of them will say free body diagram because it's just so ingrained into their brain. But we're going to start out, first of all, just looking at how we can apply some of what we learned already. Recall, Newton's second law was F equals what? ma. A spacecraft has a mass of 3.25 times 10 to the fourth kilograms. Its engine can exert a thrust force of 7.25 times 10 to the fourth newtons. Cool. What does part A want me to find? You look like you're zoning out. You back with me? I know. What's part A asking? At what rate will the spacecraft what? Okay, it wants us to find acceleration. Cole, do you see a VF or a VI or a D or in fact, do you see a mass? This is our hint that we're going to use Scott's theorem. So we had F equals what? ma. Scott, get the A by itself, please. Sorry? Okay, so we can go like this. A equals F over M. So, wow, I have my pen writing weird. So it's going to be the force 7.2. What is stuff vanishing? Let's try closing this program temporarily. I think we're going to try closing this program temporarily. And then let's try bringing it back, Mr. Dewick. Because for some reason, stuff wasn't sticking around. A equals F over M. There we go. So the force is 7.25 times 10 to the fourth, all over 3.25 times 10 to the fourth. What do you get? Mr. Dewick, can I use the do you see? Would the 10 to the fourths cancel out? You know what? That's a good point. Mallory, they would actually cancel. I could just go 7.5 divided by 3.25, 7.25 divided by 3.25, which is probably less typing, so I'm going to do that. And I get an acceleration. Y'all get 2.23? Okay. Units? Cole, units? Go. I thought you forgot the squared for a second there. Meters per second. Squared. Okay, good. Okay. So, suppose the spacecraft maintains this constant acceleration for 45 minutes. Nice try, Dewick. First thing I did is I crossed out 45 minutes. What am I going to do with that? Okay, how do I convert minutes to seconds? And you'll notice we can build a chain and write down what they gave, like we did at the beginning of the year. But now I'm starting to say for some of the more common ones, it's nice if you develop a bit of a shortcut. It's okay. How do you convert minutes to seconds? Braden, loud and proud. I totally agree with you. So I'm going to go 45 times 60, 2,700 seconds. Before turning off the engine, and its initial velocity was 5.6 times 10 to the 3, what will the final velocity of the spacecraft be? Okay. I kind of remember this. Zaina, what's this asking me to find? Oh, you know what? I'm going to fall back on my DFIC approach. I'm going to go VF equals question mark. What's that 2,700? Uh-huh. Oh, remember how easy this was? What's that 5.6 times 10 to the 3? Gotta be. What else do I need to find VF? What did I find in part A? Okay, so as far as I'm concerned, it would be fair game for me to only give you part B, not ask you part A, and expect you to clue in, I need to find the acceleration. Hey, they gave me a force and a mass, I can find the acceleration. So here I walked you through it, but I think it would be fair game for me to just go straight to part B, skipping part A, and expect you to have the aha moment yourself, okay? So A equals, I'm going to write 2.23, but you know I'm using my answer button. Oh, which equation? Zaina, my joy. Yeah. It's going to be 5.6 times 10 to the 3 plus 2.23 answer button times 2700. 5.6 scientific notation button to the 3 plus 2.23 times 2700. And I get, you get 11,000. Oh, I used 2.23. I didn't use my, after all that bragging, I didn't even use my answer button. Well, that was silly. Let's do this. Let's bring that back. There's my answer button. And now I can go 5.6 scientific notation 3 plus answer button times 2700. If you use your answer button, you get 11,623.07. You know what? Let's call it 11,600, regardless. Units, Zaina? Good. Cool. Cool. Kara, what's part C you want me to find? How far? Which one is that? Distance. Which equation? I'm not going to relist everything. I've got it all listed here. How can I find distance? Uh-oh, got to get the green sheet out. Uh-huh. Oh, and I made a double check. It's the same amount of time. Yes? We're all good? It's the same amount of time. So, which equation? I didn't realize you're following. Are you following? Oh, there you go. Oh, there you go. You can learn physics. Yeah, go ahead. Pick one with D in it. I think I would probably go with D equals VIT plus a half AT squared, because the D's by itself, I got A, I got T. VF might have been wrong if I made a mistake, but no matter what, I'm having to use an answer to find an answer, so maybe I just got to get over that. I'm going to go with D equals VIT plus a half AT squared, where VI was 5.6 times 10 to the 3. T was 2700 plus 0.5. Now I am going to use 2.23, not my answer button, and 2700 squared. This should be a fairly big distance because our final velocity was 11,000 meters per second. That's like 11 kilometers per second. That's pretty fast, and we're traveling for over 2,000 seconds. I'm expecting a big answer here. Kara, what'd you get? Oh, I'll type it in as well. Racia. Don't forget the squared. Do y'all get that? Or am I wrong? I typed that in a hurry. People nodding? I don't want to write. I think this I'm going to write in scientific notation. I'll go to 3 sig figs. 2.32 times 10 to the 1, 2, 3, 4, 5, 6, 7. Or if I want to put that in kilometers, I'll just divide by 1,000. In 45 minutes, we've traveled 23,000 kilometers. Yeah, we're a spaceship. We're moving. Okay. Amelia, what will the velocity of the spacecraft be after 90 minutes? Or after 60 days? Or after 4 years? And your hint is, you already know the answer. Oh, now I'm messing with him. Can you go back and find something that I underlined? Somewhere I underlined something in the notes. No, don't go back. No. In this question. I underlined something somewhere. What did I underline?
Turning off the engine.
What?
Turning off the engine.
Again, what?
Turning off the engine.
How fast is he going after 90 minutes or 60 days or 4 years?
Same speed.
What same speed?
2.3.
Which same speed?
Oh, so yeah. 600.
Newton's first is going to kick in for the rest of this spacecraft's existence, as long as they don't run into any other gravitational fields or planets, and as long as they don't turn their engine off or on. They'll keep coasting. This is one of the nice things about spacecraft. It's very difficult to get objects into space, but once you have objects in space, it's not that hard to get going somewhere else. For example, to get to the moon, we only used the engines to get about halfway there. Then we shut them off and let the moon's gravity pull us the rest of the way. We just coasted. Okay. Mars would be something similar. It's not halfway because moon's gravity is not as strong as Earth's gravity. It's actually a little further. But basically, you fire your engines, you coast, you're slowing down, and then all of a sudden you start to speed up. That's when you've got close enough to the other planet that its gravity is stronger than Earth's gravity, and you start to speed up and speed up and speed up. Here, though, we're in the middle of outer space with no gravitational fields, so you'll keep going in a straight line at a steady speed. That was just to get you thinking. Now we're going to get to the lesson part, so sit up and pay attention. A free body diagram. I abbreviate these as FBDs, free body diagrams. What's a free body diagram? It's a picture where we represent the object that we're looking at, the mass that we're looking at, with a little dot, and any forces acting on the object are represented with arrows, aided roughly to scale. And what do I mean by roughly to scale? If you know one force is bigger than another force, make the arrow obviously longer than the other arrow. If you know two forces are the same size, eyeball them, make the arrows the same size. So you don't need to use a ruler and measure, roughly to scale. Okay? You guys here? You're all standing in the hallway. You here? You with me? Okay. And then we're going to use Newton's laws to figure out which forces are acting on the object. Let me give you an example. Free body diagrams for 4 situations are shown below. The net force is known for each situation, but the magnitudes of some of the individual forces are missing. I'll zoom in on this first one here. I'll show you how we'll do this. Mallory, what does it say F net, the overall force is? That means forces must be, I'm looking for a word that starts with letter B. Okay, if we're pulling to 50 newtons to the right, how big must A be exactly if forces are balanced? Has to be. Must be. Oh, how big must force B be? Has to be. Must be. Sophie, I'm going to be a bit of a tougher one. Sophie, what's the net force, magnitude, and direction for the second diagram? And direction? 900 up. Okay, 200 down. How big must C be so that we end up with 900 up? Yes. Has to be. Is that what you said? Did you say 700? No, 1100. 900, 200 down, 1100 up. The net force has got to be 900. Should have just gone with it. I wouldn't have heard because they rhymed. Ooh. A little tougher. Maddie, what's the net force here? Magnitude and direction. Sorry. Yeah. Read it to me. Net force, magnitude, and direction. Okay. We have 80 newtons to the left. How big must that be so we end up with 60 newtons to the left? Yes. Is there any up-down force? Does it mention any up-down force in the net force? So that means up-down forces must be, I'm looking for a word that starts letter B. How big must E be? Has to be 300. Fahim, what's the net force in this last one? Magnitude and direction. So how big must force G be exactly? You're right. Yes. Is there any up-down net force? How big must force F be compared to force H? Okay, so I'm going to say F equals H and H equals F. I can even be generic like that. So a free body diagram helps you see how all of the forces fit together. Example 3. A book is at rest on a tabletop. You know what? The binder sitting in front of you on your lab table. Draw a free body diagram for that. First of all, we're going to represent the book with a dot. I'm going to teach you a method. We are going to go very systematically. You are going to be tempted to always want to rush to the toughest, trickiest force right away. Do not. I'm going to force you to go systematically in order. And if you do that, you'll find the complicated one becomes obvious by the time you get there. So you're going to hear me start to say some phrases, and you're going to hear them about 1,000 times between now and the rest of the year. So you ready? It goes like this. What are the forces acting on this binder? Get the obvious one. And by the obvious one, I mean the thing that's holding you to the earth. Gravity. Draw an arrow pointing down and label it Fg for gravity, force of gravity. Now look at your binder. Is it sinking into the ground like quicksand? Is it flying to you like Superman? Is it accelerating? That means forces must be, I'm looking for a word that starts with the letter B. So there has to be an arrow pointing up exactly the same size as you drew the arrow pointing down. Eyeball it. Mine is about like that. However long you drew yours. What force is that? What is pushing up? You're right, say it. F table. Now we're not used to an inanimate object applying a force, but it has to be. If it wasn't, your book would not be sitting at rest. Okay? Oh, if you want to get these wrong, draw your free body diagrams like this. If you draw them small, you're going to get them wrong. In fact, I even don't like how small I drew this. I'm making a mental note to put way more space there. Example 2, draw, what's FBD an abbrev for? Free body diagram. For the following masses hanging from a rope. Okay, so I'll do this one right there. There is the mass. What are the forces acting on it? Get the obvious one. What was that? Gravity. So whenever I say get the obvious one, everybody, get the obvious one. Everybody, get the obvious one. That wasn't everybody. Everybody? Okay. We're going to draw an arrow pointing down. We're going to call that FG. Zaina, what does it say in brackets here? So is this accelerating? So that means the forces must be, I'm looking for a word that starts with the letter B. So there must be an arrow pointing up, bigger, smaller, or the same size as gravity. Yes. Eyeball it. What's that? It's the rope. We're going to give a special name to the force from a rope. We call it tension. I usually abbrev that with a capital T. Second diagram. Mr. Duick, won't it be exactly the same? I don't know. It's a good question. It wants me to do a free body diagram for this. Okay, I'm going to represent the mass with a dot. What are the forces acting on this mass? Get the obvious one. Good. Gravity down. Ooh. Ah. Jada, which way is this one accelerating according to this question in the brackets? Which way? So I'm going to ask you a bunch of questions. They're all going to be different, but I want the same answer. Your answer is the word up. Are you ready? Which way is this accelerating? Which way is there an unbalanced force? Which way am I going to draw a longer arrow? I'm going to exaggerate it so it totally catches my eye, so it's obvious. This is why I said roughly to scale. What force is that? It's the force from a rope. What do we call the force from a rope? We just gave it a name. You're feeling some right now. Little tension. Different kind of tension. Good. Next page. Basically, if you raise your hand to ask me a question and I walk over and I don't see a free body diagram, almost always I'm just going to walk away. When in doubt, a free body diagram. It's a bit more complicated than that, and as you learn more, I'll give you some triggers so that when you can be sloppy and ignore the free body diagram, but most of the time, this is a job for a free body diagram. Some types of forces. One of the forces that you're most acquainted with is the force of gravity. This is the force that the Earth's mass exerts upon you. The force of gravity is calculated as follows. Fg equals, well, first of all, F equals what? I'm going to use M, and instead of A, I'm going to use a lowercase g as my abbrev for the acceleration due to gravity, which you all have already memorized. What is the acceleration due to gravity? And we're going to use a positive in this unit because we're going to let down be or positive be or up be what's most convenient. So here we're just finding a magnitude. Just going to put a positive 9.8 in. Did I give you that equation on your formula sheet? That's a hint to go look at your formula sheet. Yeah, I did? Okay, but can you see it's really F equals ma in disguise? This is why I said you're actually only going to get one equation for this whole unit. It's F equals ma. But what's another word for the force of gravity, Zaina? It says it, I think. It says it in the formula sheet, doesn't it? What? No, now. Wait, no, now. Wait, no, now. That's a joke. A little pun there. Okay? You're supposed to be laughing hysterically, right? Jeez, tough audience. Another word for the force of gravity is weight. And I'm telling you right now, there will be questions where I say find the weight. And if it's multiple choice, one of the answers will be the mass. Don't be telling me the mass when I want the weight. Weight is a force. And so because it's a force, it's measured in... What is force measured in? What are the units for force? You know this from yesterday. Oh, Jada's trying to brush the car. Help her out. Help her out. What are the units for force? Weight is measured in newtons. It is not measured in kilograms. Mass is measured in kilograms. Weight is the mass times the acceleration due to gravity, and it's measured in newtons. Weight is a force. Mass is not. And I'm going to be fussy for the rest of the year on that. Example 3. Example 3. Jonah, what does example 3 want me to find? Find the what? No, now. It's so funny. So find the weight. On the Earth and on the Moon. You know what? I'll do part A right here. I'll do part B right here. Jonah, what does it want me to find? Which is another word for the force of gravity. So I'm going to go like this. Fg equals mg. Fg equals mg. Now, you know what? Those might look like identical equations, so I'm going to add a subscript. On this g, I'm going to say Earth. On this g, I'm going to say Moon. What is the mass of this object? What's the g on the Earth? You've memorized this one. Good. So the weight, the force of gravity on this object on the Earth is 35 times 9.8, which is what? I do this in my head. It's going to be 35 times 10. It's going to be 350 take away 7. Is it going to be 343? Double check me. Am I wrong? Is it 343? Units. Jada, it's a force. Units, it's a force. Newtons. No more panicking. This part we got to start to memorize now. I know. What about on the moon? It's still going to be 35, but what's G on the moon? Jada, your hint is, I told you next to part B in brackets there. Okay? You don't need to memorize that. If I ever do a question on the moon, I will give you that piece of information in the question. So the force of gravity on this object on the Earth will be 343 newtons. The force of gravity of this object on the moon, I can do this in my head, it's going to be 35 plus 7 plus 7 plus 7. It's going to be 35 plus 21. Is it 56? Yes? What are the units for force, Jada? There. So this is why the astronauts were able to function on the moon. They were wearing spacesuits that had a very, very heavy mass on the Earth and a big force of gravity on the Earth. They didn't lose mass on the moon. They lost gravitational force. They lost weight on the moon. And that's why they were able to wear these heavy spacesuits and function on the moon. Your mass doesn't change. Your weight changes. Your mass is the same anywhere in the universe, even near a black hole. What does change? The one that depends on the force of gravity, which starts with the letter W. What changes? Not your mass, but your... No, now. Yes. Here's the big idea for this whole unit. Fahim just yawned. Sit up, Fahim. Turn your brain on. Here it is. For the rest of this unit, if we're going to solve situations involving forces, we're going to use a tug-of-war analogy. We're going to draw a free body diagram, labeling all the forces. We'll use Newton's laws to figure out if any are missing. And then we're going to use our knowledge of physics to decide which one is the winning or strongest force. Which way are we accelerating? And we're going to use the following equation. Write this down. Winner minus loser equals F net. The net force. Oh, where the net force is equal to, what does it say on your formula sheet? What is F net equal to? Yeah, I've been lying. It's not actually F equals MA, it's F net equals MA. So what we're actually going to do is this. We're going to go winner minus loser equals MA. If you take Physics 12 with me, I will not teach you anything different. This right here, with a bit of cleverness, can be used to solve everything. Show you what I mean. Example 4, I like example 4. Example 4 is a little too easy. Suppose the box is resting on ice and the following forces are acting on it. It looks like we have a 6 Newton force to the left and a 14 Newton force to the right. A says add any forces you think are missing. Okay, this is a job for a free body diagram. Although, did they give me a picture of the box? I'm going to be a bit lazy. Instead of doing a completely separate free body diagram, I'm just going to label the box. What are the forces acting on it? Get the obvious one. Okay? Now, on the previous time I labeled gravity, I wrote Fg, but because the equation for gravity is mg, you're going to notice most of the time I just put the mg. I skip the label and that's what I'm going to be typing in. So I don't care which one you do, but I'm telling you right now, without even thinking about it, I'll do that 99% of the time. Is this box sinking to the ice like quicksand? Be obvious. No? Is it flying at you like Superman? That means vertically the forces must be, I'm looking for a word that starts with letter B. So there's going to be an arrow pointing up the same size as you drew gravity, and that is the ice pushing back on the box. By the way, that force up, that's a Newton's third. The box pushes down on the ice, forces come in pairs, the ice pushes back on the box. What else? I got the 14 and I got the 6. Okay. Okay. Scott, what does B want me to find? We're going to use your theorem, but we're going to modify it. Scott, look at the picture. Which direction must this accelerate? Which direction is your unbalanced force? Good. I'm going to ask you several questions. Your answer each time is going to be the word right. Right? Right? Right. Okay. Which direction is the unbalanced force? Which way is the longer arrow if I was drawing a free body diagram? What direction is the winning direction? Okay. Which way is winning? Now we're going to write our equation. Who's winning? 14. So first of all, let's write winner minus loser equals MA. We'll start to skip that step shortly, but this is my thinking. Which is the winning force, Scott? How big? Minus. Who's the loser? Cole. I said, who's the loser? And he looked at you. Did you see that? Wow. Cole, Bonson Park, 3 o'clock. If I'm not there, I'm telling you, you can totally take him. Fine, Scott. Which force is the losing force? How big? What does that always equal? MA. Scott, what did you tell me they're asking me to find? How would I get the A by itself? Scott's theorem. So everybody, cross out the M right there, big fraction line, put it there. I will figure out if that's the work you show, I will clue in what you've done. You don't need to rewrite it or anything like that. Now we're going to plug in our numbers. A is going to be 14, take away 6 divided by... Scott, what was the mass? You do. I'm going to make you figure it out. Look at the picture. Okay. I don't know is not acceptable. Got to push you out of your comfort zone. What do you get? Oh, it's going to be 8 divided by... Is it 2.6 repeating? Yeah. Oh, by the way, probably brackets around the top or your fancy fraction button, yes? Okay. I'll go 2.67 meters per second squared. As far as I'm concerned, Scott, I can give you all of the forces and say find the acceleration, Scott's theorem divided by m. Or I can give you the acceleration and all of the forces but one, and you can find the missing force. Suppose the box below is sitting on a table and accelerating to the left at 3.2 meters per second squared. A says, add any forces you think are missing. I see one that's missing. Get the obvious one. Get the obvious one. Get the obvious one. Everybody. Fahim, get the obvious one. Thank you. I got to see lips move. MG down. Fahim, is this box sinking to the ground like quicksand? Is it flying you like Superman? So I'm going to draw an arrow pointing up the same size as I drew my arrow pointing down. And that is going to be F. I guess it's sitting on a table, so it's F table. I think we've got all of the missing forces now. This matches Newton's laws. Aiden, what does B want me to find? I'm going to call it F-Abe. In fact, I'm going to call it F-A. And I'll call Billy F-B. And you've clued in enough that we tend to abbreviate. Yes. Which way are we accelerating? Okay. I'm going to ask you several questions. Your answer each time is going to be the word left, right? The word left, right? Wow. Okay. Which way are we accelerating, Aiden? Which way is the winning force, Aiden? Who's winning? FA. Okay? So winner minus loser. I'm not going to write winner minus loser equals MA. I'm going to go straight to the equation. Which force is winning? Winner. Minus. Who's the loser? Cohen, did you see? I said, who's the loser? He looked at you and he just shook his head. Wow. Aiden, you might want to move over one chair because I think there's a little friction. Okay, fine, Aiden. Who's the losing force? What does winner minus loser always equal? What? MA. What are we trying to find? How would I get the FA by itself, everybody? Add FB. So this is why I taught you that formula manipulation 2 units ago, because there is no way I can come up with every single equation in this unit. Oh, throw another force in. Now it's totally different. Oh, have it accelerate in a different direction. Totally different now. So I'm not going to try that. I'm going to say you can rewrite this. So we're going to plus that over, and we'll get FA equals MA plus FB. And now we are at the plug and chug stage. Aiden, what's M? How did you figure that out? You were clever enough to look at the diagram and read instead of saying, I don't know, right? Right. You missed the hint. Okay. What's A? I bet you the question told you somewhere. What's A? I bet you the question told you somewhere. 3.2. Mr. Dewick, it's to the left. Shouldn't I make it negative? Actually, we decided to make to the left positive because it made the math easier. And that's what you're going to find in this unit. We're going to let positive be whatever makes the math easier. We're going to get away from down is always negative and up is always positive. That's for amateurs. We can do better. And then plus, what's FB? Good. What do you get? 40 even? Units, Jada, it's a force. Acacia, sorry. Units, it's a force. There you go. Okay. Starting to see why a free body diagram and winner minus loser is really useful. We're going to finish and then hit pause with example 6, and then I got a video to show you. Example 6. I like example 6. I like example 6. Example 6 is a nice question. Ella, what does it want me to find? You're probably feeling a little tension right now. Different kind of tension. This is a job for a free body diagram. Now, how do I know that? What does it want me to find? That's one force. Get the obvious one. Get the obvious one. If there's more than one force in the question, that's a job for a free body diagram. You will rarely go wrong if you notice there's more than one force to draw a free body diagram. I'm going to draw my free body diagram right there. What are the forces acting on this, Emma? Get the obvious, Ella, get the obvious one. Sorry? Loud and proud. Good. Did I call you Emma earlier accidentally? I hope not, because I'm trying to do better than that. What else? You're feeling it right now. A little tension. Is tension going to be bigger, smaller, or the same size as gravity? And how do I know? Why? That's the power of Newton's first. The fact that I know that it's accelerating up tells me there has to be an unbalanced force in that direction. I'll exaggerate it so it's obvious. Don't do something like this. Gravity, tension. Oh, that tension's long. Make it obvious. Do yourself a favor. Who's winning? Who's losing? What's that always equal? Tension minus mg equals ma. Don't try and memorize this equation. You'll derive it from a free body diagram because there's going to be a bajillion equations. What am I trying to find? Okay. By the way, I could also have given you the tension and say find the acceleration. We would use Scott's theorem. But here, they're giving me the acceleration. How would I get the t by itself? Tension is going to be ma plus mg. Did they give me m? What? You mean it's somewhere in the diagram? You don't need to say I don't know before looking? Okay. Did they give me a? What? Plus? What's g? Mr. Dewick, is it 9.8 or negative 9? This unit, it's just going to be 9.8. Can you see, we put the negative right there when we did our winner minus loser. We took care of whether it needed to be negative or not, just fine. So we don't need to put a negative in for the 9.8 itself. It's just going to be like that. What do you get? Can I do this one in my head? Maybe. It's going to be 12 times 11.8. 12 times 11 is going to be what, Mr. Dewick? 132? 132 plus 7.2. 139.2. No, I'm wrong. Am I right? What is it? 142? Even? 141.6. Is that right? Yeah? I don't trust him. Okay. 141.6, which is all round to 142 newtons. Oh, newtons because it's a force. Pause here. We're going to ask a question. The question we're going to ask is, why does the Earth spin? Does the Earth spin? I think I yelled at you earlier this year that Earth is round. It is round. Get over it. Earth is a sphere, or pretty close to a sphere. It's not a perfect sphere. It bulges just a tiny bit at the equator. It's a little bit shorter on the north and south poles, so it's not a perfect sphere, but pretty close. And it spins. Why? Put your pencils down, look up. That's what I'm looking for.
So I'm down in West Vancouver, British Columbia, which is...
Hey, West Vancouver, British Columbia.
Is where I grew up. And at the local beach, there is this 2.5-ton granite sphere.
You may have seen it if you've walked along the beach by West Van.
It was made to have a tolerance of 0.02 of a millimeter. This is an amazing granite sphere, and it's floated on a thin layer of water. And it just presents an amazing opportunity to study inertia. And that's why I'm down here.
So it's a granite sphere. You can see it's actually got a map of the globe on it. There's also one in Tomorrowland, in Disneyland. There's a few of these. It's a fairly popular, expensive sculpture. It's very, very finely machined, and it's floating on a very, very, very thin sheet of water, which means it's nearly frictionless. Almost perfectly frictionless. Not quite.
To have a chat with some of the people going by about why the globe spins, and in fact, why the Earth spins. Why does the Earth spin? Why does it turn like that?
I think it's the gravity, right? For it to keep us down on the ground. Is that right?
Gravitational pull.
Well, how does that cause the Earth to spin?
Again, my basic science fails. It fails gravity, and he...
Is gravity what makes the Earth spin? See some of you shaking your heads. I see some of you nodding.
guesses, looking...
Gravity. Oh, yeah, gravity.
It's not stopping. Would you agree with me?
Yeah.
So why is that?
Some sort of force that's...
You think there's a force down there pushing it?
Yeah. I'm going to go because the upthrust from the water is probably angled in such a way that it's, because it's a spherical shape, it's probably pushing on it at an angle, so it spins constantly.
Yes, what is the centrifugal force that keeps it going? What is that force? And where does that force come from?
Is there a force that keeps it going? Is there a force pushing it around?
Within.
Once an object is moving, do you need a force to keep it moving? Cole, was that a head shake or was that a just stretch in the neck? Or was that a little column A, a little column B, and you have no... What does Newton's first say? Once an object starts moving, what? It's going to keep moving. I don't think you need a force to keep the Earth spinning. I don't think you do. The Earth spins. Nothing pushing it.
Within the Earth's core, is there not something that drives and dictates said centrifugal force?
There's no force that makes it spin.
Guess it's the law of inertia, isn't it?
Ooh, the law of inertia, isn't it? What's the law of inertia? Why, that's Newton's first. That's the one that says once an object is moving or spinning, it will keep moving or spinning at a steady speed, as long as no other unbalanced forces are acting on it. Since the Earth is sitting in outer space, don't think there's too many unbalanced forces acting on it.
What's the law of inertia?
Every action causes equal and opposite reaction.
That's not Newton's first. Which one is that one?
The force of inertia maintains this.
But inertia, which is a great idea, is not a force.
How would you define?
It's just the tendency of all objects with mass to maintain their state of motion.
Okay.
So if they're stationary, they want to stay stationary.
And
If we anthropomorphize them.
Yes, and if they're moving, said anthropomorphized objects want to keep moving.
Basically, whatever motion they have, they like to continue in that state of motion.
Yes.
So the Earth does that without any forces. This does that without any forces.
Yes.
Yeah.
So why does the Earth spin? It spins because the dust that formed it billions of years ago was spinning. And nothing has been able to slow it down. There's no force acting to slow it down. We call that inertia. I lied a little bit. The moon is slowing us down ever so slightly each year. Eventually, a few billion years from now, the Earth and the moon will be locked tidally, which means in the same way that the same face of the moon always points towards us, the same face of the Earth will always point towards the moon. But I'm not going to be around then, so it's not too big a priority a few billion years from then. What's your homework? You have lots to work on from last day. Okay?